The purpose of this video is to begin to give you some advice about how to take a standard spectral set of problems and go about solving the structures. There's no one way to do this, but I think if you keep things in this presentation in mind, you'll find that things are a good little bit easier to at least get started on. So let's once again define the scope of the problem. In general, you're going to have the molecular formula, the IR spectrum, the carbon NMR, the proton NMR, and your task is to solve for the structure. This requires practice. The more you do, the better you get. There'll be some things that you recognize you don't even have to think about and put things together. In general, there are some pretty standard ways to get started, and that's what we're going to try and concentrate on in this presentation. Keep in mind what we're doing. The formula gives you a whole bunch of atoms, and they have to come together somehow to give you a structure. The standard valencies, to use an old-fashioned word, which you're aware of, that hydrogen only makes one bond, carbon generally makes 4 bonds, and those sorts of things, put some limits on the way the atoms come together, but if the formula has a reasonable number of atoms, you're going to have a lot of possibilities, and you can't just examine all of them and come up with there. What the Spectral will do is give you some information on what atoms are connected to what and in what way. And so you're taking those pieces of atoms and making bigger pieces. Just like a jigsaw puzzle, the bigger the pieces get, the fewer variables there are to come together to give you a structure. In the end game, one of 3 things could happen. The first is that you've processed all of the information and you've gotten one big piece and there's your structure. That's generally a pretty easy problem. More often you'll have a set of bigger pieces and you'll look at them and puzzle them, and using your chemical intuition you'll recognize that there's only one way they can come together, and that's your structure. The other alternative is there are several ways they can come together and you need more information, and there are other spectral techniques, but for this course we're going to try to stick to problems that can be solved with this amount of data, which is really quite a few structures. The point is there's no one way to solve a structure. There are many places to get started. We're going to show you several places to get started. You can get started in all kinds of different orders, but generally once you get started you'll then engage the problem and begin to do the solution. So how do you start? Most important way to get started is to write down things that you know have to be right. If you start off with a bad assumption, you'll wind up spending a lot of time before you recognize that, and so make sure you're safe at the very beginning. Safest thing to do is to take the formula and calculate the degrees of unsaturation. That's something that you can do quite quickly. Next thing that I'd recommend you do is look at that formula, see the number of carbons, and compare that to the number of peaks in the carbon NMR. In that way you'll find if there's any symmetry involved in there or if all the peaks are there in an array. At that point then it's a good idea just to take a very quick look at the IR. I wouldn't act as if you only had IR information, but you can look at the quick stuff first, knowing that you can go back later and check out things. And of course those are the regions we looked at in the past: 3300, 3000, 2200, and 1700, to give you lots of information. The next thing to do then is confirm that the integral numbers in the proton NMR, that is to say those area peaks, account for all the protons so that everything's there in front of you. Once you've done that, you're in a good place to begin to get started. So the 4 most important starting points are the unsaturation, the heteroatoms. Remember, heteroatom means that it's not hydrogen or carbon. Generally that's going to be an electronegative atom. Methyl groups are going to be very important, and symmetry that you get from the carbon NMR. I'm going to present these things in some sort of sequence, but recognize that this is an exercise in parallel processing. You'll jump back and forth from one spectrum to another to confirm information you've got on one, pick up a new piece, go back to the old data now that you have that piece, and put things together. The other thing you should remember is that you are looking to solve a structure, not to explain every peak. Some areas, particularly in proton NMR, can be very complex, but if you can solve the structure without diving into them, you don't need to care too much. there's always a good last step. Once you think you have a structure, go back and make sure that the spectrum is consistent with that structure you proposed and that all peaks are present and accounted for, and there are no extra peaks that are going to contraindicate the compound you have chosen as your solution. So let's go back to unsaturation. Remember how to calculate units of unsaturation. The units of unsaturation is the number of pi bonds plus the number of rings. So the first thing you'll want to do is figure out how many pi bonds you have. C double bond O and C double bond C are typically pretty easy to find in the IR and the carbon NMR, as are alkynes and nitriles. And so that's a pretty easy way to begin to get a count of your number of pi bonds. Once you have all the pi bonds counted, the remainder of the unsaturation is rings, and you'll need to keep in mind that if you're going to get the right formula, you're going to need to have a ring somewhere if it is required by your degrees of unsaturation. Another good thing to keep in mind is that if your degrees of unsaturation is greater than or equal to 4, you may well have an aromatic ring. And that would require a good peak at the region around 7, because that's where aromatic rings come. So if you have a degree of unsaturation of 4 or more and you have peaks in the region around 7, you might draw a benzene ring. There are other aromatic systems besides benzene rings, but that's a good place to get started. The multiplicity around the aromatic ring and the array of peaks may be complex, but you may not need to solve for those. Because if the integral at 7 is for 5 protons, then your benzene's monosubstituted. You don't need to solve every peak that's in there. There's 5 protons on your benzene ring, and there's one thing that's not a proton, monosubstituted. If the integral is 4, you can easily ID the parasubstitution by symmetry. You'll have fewer peaks in that aromatic region in the carbon NMR than there is formula. Ortho and meta substitution is tougher to do, and oftentimes you'll not be able to define that without really going into the splitting and multiplicity pattern more deeply than we want to in this course. If the integral is 3 or less, the problem is trickier, but you can defer substitution pattern in the end. Just know you have a benzene ring with the correct number of hydrogens, and concentrate is what on those other carbons in the ring. Alkenes are also easy to find. You can find alkene hydrogens in the proton NMR, and then you can count the number of protons on that or those double bonds. Remember, that's the region from about 4.5 to around 6, well separated from the aromatic region. If you have a CH2 double bond CH, you're going to see a very complex pattern. But remember, if you have a CH2 double bond CH, you're going to have an integral of 3, and you're not going to have to do any more. That's the only way a single double bond can have 3 hydrogens on it. If you have a CH double bonded to a CH, they're going to split one another unless they happen to be chemically equivalent. As an aside, splitting can often distinguish between E and Z double bonds if they're evident, but remember, there can be things on the other side of those CHs that'll also split those hydrogens, so you can actually get to pretty complex spin patterns or splitting patterns. If you have several different C double bond Cs that are not a benzene ring in the molecule, things get a bit tougher to put all the pieces together. I'd recommend that you make note of that and go on to other data before going too deeply into solving that structure. Remember, you don't need to get everything at the first dive. Get good information. Go elsewhere and watch this thing assemble. Let's go on to heteroatoms. Heteroatoms are a really good handle. For example, if you consider oxygen, oxygen can only be bonded to 2 things. If oxygen is bonded to the same carbon, that's a C double bond O. You know how to find that. If there's no C double bond O, then your oxygen is either flanked by 2 carbons or a carbon and a hydrogen. It's easy to find that hydrogen in the IR, and you can find carbons directly bonded to oxygen in carbon NMR and proton NMR. Those will be the signals, or the hydrogens in the proton NMR will be those signals at around 4. If there are 2 oxygens in the formula, you know how to identify acids and esters in the IR. if they are in two very different parts of the molecule, you're going to have combinations of those peaks. And so you'll need to puzzle that out, find out where your oxygens are, and those are very good handles. Nitrogen can only be bonded to three things. You can easily spot NH and NH2. If there's oxygen in the formula, you can also easily find amides. But that'll give you a piece. Starting with your nitrogen, you'll see what other things are attached to it. Methyl groups are great because they're easy to find and they're easy to interpret. A methyl group can only be attached to one other thing. Right? And you're going to find those by seeing that if you have a methyl group, you're going to have an integral that is a multiple of 3 and has a clear coupling pattern. A CH3 must have a shift below 4.5 because it can't be an sp2 carbon up there in the 4s. It can't be part of a benzene ring. It's a CH3 that's only attached to one thing. And so if you see 3 protons at 7, that's 3 hydrogens on a benzene ring, not a methyl group. Okay, once you've seen a methyl group there on the right-hand side of your spectrum, if it's bonded to a heteroatom, the shift is going to be in the 3 to 4 region, depending on the heteroatom. Oxygen's in the low 4s, nitrogen will be in the low 3s. This will depend on electronegativity. But in any event, your peak for the methyl group bonded to a heteroatom is going to be a singlet because there's no hydrogens for it to be coupled to. If it's attached to another carbon, it'll either be a singlet, a doublet, or a triplet, depending on whether the carbon is attached to has 0 hydrogens, 1 hydrogen, or 2 hydrogens. Can't have 3, that's ethane, and it's just a single molecule. If your methyl group is attached to an sp2 carbon, the shift will be around 2. If it's on an sp3 carbon, it'll be around 1 to 1.5, sometimes a little under 1. All right then, so let's recap. Recap is you find a methyl, you can find the next thing attached to that methyl. Using your unsaturation, you can find a benzene ring and how many things are attached to that benzene ring, or C double bond Cs, or C double bond Os. Starting at your heteroatoms, you can either get double bonds to those heteroatoms or see the things that are attached to it and then move on from there. This was a quick review, but they are a good way when you start doing problems to begin to get started on things. Subsequent videos will do some problem-solving exercises, and as a result of those problem-solving exercises, you can see how this actually begins to work in practice and begins to allow you to solve structures.